All right, so let's go through this. Obviously, you wouldn't have a problem this long on the exam, but maybe part of a problem like this. Maybe I'd ask you, instead of finding all the numbers of elements of the various orders in S5, I could ask you, find the number of elements of order 4 or something like that, or 2 or 6. 2 is actually a little extra tricky, because you got to remember, not only do 2 cycles have order 2, but the product of 2 disjoint 2 cycles would have order 2 as well. So you got to think about a couple of cases there. So I'll do my scratch work down here. You got a plain old 2 cycle. I'll just label the entries A and B. You've got 6 choices for what can go there, or excuse me, 5, because we're in S5, and 4 choices for what can go there. Does that mean the number of these kinds of elements is 5 times 4, 20? Here's the first tricky part. I see people shake, a few people shook their heads. That's correct. It's not 20. It's 20 divided by 2. It's 10, because for each way you write it like this, it's equivalent to writing it like this. So that would be 5 times 4 divided by 2, 10. But it's even a little more tricky, because you got to think about products of disjoint 2 cycles, where A, B, C, and D are all different numbers, 1 through 5. For the first one, you've got 5 choices for the first one, and then 4 for the next, but you can write that in either way, either AB or BA. So you got to divide that by 2. For the second one, because these are disjoint, you've got 3 choices left for C and 2 choices left for D. But again, that can be written in either way. So divide that by 2. But then there's one more tricky thing here. What's the one more tricky thing?
You divide by 2 again, because you could flip-flop the A, B, and C.
Right, disjoint cycles commute. And these, in a sense, these are indistinguishable from each other, because they're both 2 cycles. You don't quite do the same thing when you think about the elements of order 6, because the cycle lengths are different, 3 and 2 in that case. So you got to divide by 2 again. I'm writing it like that. The book writes it all as one fraction, which we certainly can do. 5 times 4 times 3 times 2 over 2 times 2 times 2. Get some cancellation. This looks like it's 15. And write the same thing up here. 5 times 4 times 3 times 2 over 2 times 2 times 2. It's 15. The other one again is 10. 10 plus 15 is 25. Did you get 25? So now we're up to 26 elements. That's our running total. How many cyclic subgroups of order 2 are there then? And yeah, okay. That's relatively easy. It gets a little trickier with order 3. Each element of order 2 generates a cyclic subgroup of order 2 that's distinct from all the other cyclic subgroups of order 2. Because it's the 2 elements would be the identity and that given element of order 2 in each one. So they're all distinct. So you'd have 25 cyclic subgroups of order 2. Elements of order 3 would have to be 3 cycles and nothing else, because if you multiply it by a 2 cycle, it would no longer have order. A disjoint 2 cycle would no longer have order 3. If you multiply by 1 cycle, well, 1 cycles keep things fixed, so that really doesn't do anything. This one's actually a little easier to think about. but there's still a little bit of trickiness to it. So you got 5 choices for A, 4 for B, 3 for C, then divide this by what? 3, not 2. Because each such 3 cycle can be written in 3 different ways. Altogether giving you 20 elements of order 3, so we're up to 46 elements. And how many cyclic subgroups of order 3? A little trickier than the one for 2. There's 10, yeah. 20 divided by 2. 10 for each cyclic subgroup of order 3. There's going to be 2 non-identity elements. And those 2 non-identity elements cannot be in some other cyclic subgroup of order 3 because they're generators for that given cyclic subgroup of order 3. So the intersection with some other cyclic subgroup of order 3, it's just got to be the identity. Because if they had anything else in common, they really would be the same cyclic subgroup of order 3. Order 4 can occur that way. Can you get an element of order 4 in any other way? No. If we were in thinking about elements of S8, which has 8 factorial elements, which is really, really big, you know, thousands and thousands of elements, there'd be 2 ways to think about elements of order 4. A, B, C, D, and then another 4 cycle, E, F, G, H, if we're talking about S8. In S8, there would be a lot more elements of order 4 than there are here in S4, S5, S6, S7. Those all have the same number of elements of order 4 because you can think about it in the same way. 5 times 4, oh, they won't have the same number, excuse me, because the numbers on the top of the fraction are going to be different. Divide by what? 4, because there's 4 ways to write that. So that leaves us with 5 times 3 times 2 is 30. Up to 76 elements. How many? Okay, this is a little trickier yet. How many cyclic subgroups of order 4? Got to divide by the number of generators of a cyclic subgroup of order 4, not the number of non-identity elements. So do I divide by 2 or 3? Divide by 2, yeah. A cyclic group of order 4 has got 2 generators. Think about Z4. Its generators are 1 and 3, not 2. 2 generators. I divide by the number of generators. There's 15 cyclic subgroups of order 4. There could be conceivably some non-cyclic subgroups of order 4. Talked about that on Wednesday. There is a group of order 4 that's not cyclic. Only one up to isomorphism, but that's there. But we're talking about number of cyclic subgroups. 5 times 4 times 3 times 2 times 1 divided by 5. 24. So that brings us up to 100 here, it looks like. Hopefully no mistakes so far. How many generators does a cyclic group of order 5 have? Think about Z5. Somebody want to say? It's got it. Divide by 4 actually. cyclic group of order 5 has 4 generators. Think about Z5, the generators are 1, 2, 3, and 4. All the non-identity elements, because 5 is prime. Phi of 5 is 4. This is 6. With 6 elements of order 6, we think about disjoint cycles where one of them is a 3 cycle and one's a 2 cycle. Five times 4 times 3 over 3 for the 3 cycle. 2 times 1 over 2 for the 2 cycle. And I don't need to switch to divide by 2 again, because these are, when you're thinking about the product of two cycles, they're what's called indistinguishable. These have different lengths already, so switching them around, yeah, it doesn't change the nature of the permutation, but you're also thinking about it in such a way that you're getting all of them here right now. I don't know if that's a good explanation, but this is 20, and hey, yeah, it brings us up to 120 as it is, so you knew it had to be 20. Any cyclic group of order 6 has got 2 generators. Think about Z6. The generators are 1 and 5. They're relatively prime to 6. So this is going to be 20 divided by 2. There's going to be 10 cyclic subgroups of order 6. How many non-cyclic subgroups of order 6? That's less clear. Perhaps any non-cyclic subgroup of order 6 is isomorphic to D3, S3. D3 and S3 we've seen are isomorphic. That's something you might want to investigate, perhaps, after the test. After the test, you're going to investigate how many non-cyclic subgroups or non-cyclic groups there are of order 6. Maybe that's a little project you can do just because you want to, right? After the test is over, just what you want to do. Now, you probably want to take a break. And by the way, there won't be any homework to do to turn in on next Wednesday. There will be some reading to do, but no problems to turn in for next Wednesday. After test on Monday from the next class on Wednesday. I hope you find this kind of thing kind of fun once you get it. Satisfying to see that it all works out. We got 120 there. Think about S6 next if you are inspired. I think it's kind of fun. All right, let's talk a bit more about isomorphisms before we do our more general review. And I think what I'd like to do is do a couple proofs, so to speak, though I won't write them out in sentences for sake of time. Say you've got an isomorphism phi from some group G to some group G bar. By the way, since I'm doing these in class, these would be examples of things you should be able to do on the exam. Again, I'm not taking the time to write these in sentences. If I had a proof like one of these on the exam, I'd want them to be in sentences, though again, abbreviations are fine to save time. Claim phi inverse exists and is also an isomorphism. Back in chapter 0, your very first homework assignment, you had a problem where you had to define what phi inverse was and verify it was 1-to-1 and onto when phi is assumed to be 1-to-1 and onto. If I put this on the exam, would you have to do that verification, or could you just do it or just say it? If I asked you to verify it, maybe I wouldn't. Maybe I would, maybe I wouldn't. If I asked you to verify it, you should be able to. How to show it's one-to-one. Assume phi inverse of, I'm going to call elements of G, I'll use the letters A and B. And for G bar, I'll use the letters C and D. Suppose phi inverse of C equals phi inverse of D. Does that imply C equals D? I guess I wouldn't ask you to define what the inverse function is because we did that before and that's understood. Well, basically it's just apply phi to both sides and then use the fact that they're inverse functions. And this implies C equals D, done. Because that's what inverse functions do, is they undo each other. Assuming we've defined phi inverse correctly to make this happen. And again, you did that on a homework assignment. So it's one-to-one. Is it onto? Give me some A and G. Is there something in G bar that gets mapped to A under phi inverse? Sure. Phi of A does. Use the fact that phi and phi inverse undo each other in the other direction. So essentially this line is one-to-one, this one's onto, though again, you'd want to briefly explain, and essentially the explanation is definition of a function and its inverse and what the property they have. Since phi inverse is the inverse of phi, that kind of thing. How about operation preserving? That might be the most important thing to focus on. And maybe if I put this on the test, I'd say just prove it's operation preserving. OP stands for operation preserving. Also stands for Ocean Pacific. Have you heard of that clothing line? It's an old clothing line, Ocean Pacific, from back in the 80s. I don't know if they're still around or not. That's what I always think of besides operation preserving. I think of Ocean Pacific. So I had some of their clothes. So the goal would be to prove phi inverse of CD equals phi inverse of C times phi inverse of D for any C and D in G bar. You're doing it for all C and D in G bars, so you'd start the proof by saying, let C and D be arbitrary elements of G bar. And if you can prove it for arbitrary elements, that means you've proved it for all set elements because they're arbitrary. One thing we're probably going to need to use is the fact that phi and phi inverse are inverses, just like with these two lines. And I bet, if you think about it, I bet the fact that phi is operation preserving is relevant. Because if phi wasn't operation preserving, it's just some arbitrary one-to-one and onto function, not a special function. Probably the inverse wouldn't be operation preserving either. It must be relevant. I'm trying to prove this. We don't know it's true right away. So how would we do it? Maybe we should apply phi to both expressions and see if we get the same thing, and then use the fact that phi is one-to-one. That's an idea. It's one way to do it at least. Phi of phi inverse of CD, by the fact that phi and phi inverse are inverse functions, is CD. I didn't use the fact that phi is operation preserving there. I must have to with the other one. What's phi of phi inverse of C times phi inverse of D? Yeah, there I'm going to have to use the fact that phi is operation preserving. Right? Lots of symbols. Make sure you understand the meaning. This is phi of the product of two elements that are in G that are written as outputs of phi inverse. Phi is operation preserving. We're assuming that, therefore it equals the product of phi of those individual elements. Now use the fact that phi and phi inverse are inverses to simplify this to CD. And yeah, one more thing to say here. What's the final thing to say? To give your final reason to conclude that phi inverse, this means that phi inverse is operation preserving. I did say it about a minute or two ago. Yeah, you got these both equal CD, so they equal each other. Outputs of phi equaling each other, the inputs must be the same. Phi is 1-to-1 implies what we want. I think another example worth doing. So this, what we just did was we essentially proved theorem 6.3 on page 127. It's a multi-part theorem. We essentially proved number 1. Let's also look at a proof of number 4. If K is a subgroup of G, then phi of K, wait a minute, how can you find phi of K? How can you plug capital K into phi? If K is a subgroup of G, not an element? Well, it's a trick question. You can't plug a subgroup of G into phi when you think about it in the usual way, at least. However, if you think of this in a new way as being this set, then you can. This is this by definition. This is called the direct image of K under phi. Direct image. I want to write that down. Phi of K, capital K is the direct image of capital K under phi. It's defined to be the set of all outputs phi of little k as little k ranges over capital A. Prove that's a subgroup of G bar. It's certainly a subset. Once again, we have an isomorphism from G to G bar. K is a subgroup of G, is the assumption. Prove that that implies this direct image, which by definition, again, is this set. That's what it is a subgroup of G bar. So use the one-step subgroup test or the two-step subgroup test. Do not use the finite subgroup test because it's not a necessarily finite group. You can use, again, you can use either test. If I give you a question like this in the exam, either test is fine. You don't have to use them both. Use one or the other. Typically, people think of the two-step subgroup test as being a little easier. Once you become a little bit more experienced, then the one-step subgroup is a little quicker. Oftentimes, though it sometimes is a little trickier. I'd be fine again with either method. Let me try thinking about the one-step subgroup test. Well, first of all, there's the 0 step of showing that this is non-empty. Well, it's obviously non-empty because K is non-empty. K being non-empty means there exists an element little k in capital K, so this set is also not empty. That's obvious. Oh, and we've got, here we run across the fact that there's different, the symbol for the empty set looks like a phi. Let me make it more like this. Some people, because of that, make their empty sets like that. So it's obviously not empty. All right, let's try the one-step subgroup test. Suppose you've got two elements, so I guess I should call them C and D. C and D in phi of k show C times D inverse is in phi of k. You've got to use what it means to be in this phi of k. This direct image, again, is what it's called. Direct image of k under phi. Does that mean there's such a thing as an indirect image? Well, we don't use that word. There is something called an inverse image, which when phi is invertible is the direct image of the inverse function, phi inverse. But when phi is not invertible, we can still end up talking about inverse images. That'll happen when we get to chapter 10. I'm not sure if we'll get to chapter 10 before spring break or not. I'm not remembering the schedule. Probably not. Probably it'll be after spring break, I think. You got to use what phi of k is. What does it equal? It equals this set. If C and D are in here, this implies that there exists A and B in K such that C equals phi of A and D equals phi of B. That's what it means to be in the direct image of K under phi. How does this help? Got a guess? Got some intuition to get from here to here? There's like only one thing when you think about it that really makes sense to guess as something that will get mapped to C times D inverse. Something in K that will get mapped to C times D inverse. If it's coming to you, and you're developing some intuition, don't be afraid to say if it is. Nobody? Maybe A times B inverse? K being a subgroup of G, K being a subgroup of G implies A times B inverse is in K, because K would be closed under taking inverses and closed under multiplication. If B is in K, then B inverse is in K. And we're already, well, then closure times another element of K is still going to be in K. Therefore, phi of A B inverse is in the direct image of K under phi. But what does this equal? Now use the fact that phi is operation preserving. Must be relevant, right? Don't forget to use that fact. OP implies this equals phi of A times phi of B inverse. To finish this, I need to use one other property that I actually haven't talked about yet. Phi of B inverse is the same as phi of B inverse. I haven't proved that. It's in the theorem on the previous page, part 2 of this theorem. For every integer n and for every group element A in capital G, phi of A to the n power is the same as phi of A to the n power. That can be proved by induction when n is greater than or equal to 0 to 1. It's obviously true when n is 0. And you could probably use a trick in the fact that it works when n is positive to show it also works when n is negative. Or maybe even use induction again when n is negative. There'd be a way to do that. In particular, it works when n is -1. It works with inverses. phi of A inverse equals phi of A inverse. And that does it, because that equals C times D inverse. C times D inverse is the image of an element of K. It's the image of AB inverse. It's the output when you plug in AB inverse. Okay, let's do our general review. Like I said, I'm going to start writing. I've got to write the exam pretty much today because of the weekend. And I'm going to write it really without looking at the old exams that I put on Moodle. So I come at it fresh, but again, I said, you know, it will have a similar feel, I imagine. I think I do want to purposely, so let's start off by saying this. I do want to purposely take some of the old quiz questions from 3 years ago, put those on the exam as true, false, and or multiple choice. Maybe change the wording a bit. That could change the answer. And then also change the order of the answer options, perhaps. Or make the example slightly different. How many of those will I put on there? I don't know. Maybe 4 such problems as a rough guess, 4 or 5. So I think I want to make a point of doing that. I think I also want to make a point of picking some of your practice problems. 1 or 2 or 3 of them. And put those on the exam. Those practice problems often involve calculations, so it could be a calculation problem. Once in a while, they involve a proof. Not ruling that kind of thing out. You should at least skim through the practice problems and think about them, even if you don't redo them from scratch. And you should think about the old quiz. And the old quiz, I'm purposely not giving you answers for, because you really should be able to figure it out, especially when you've got time. And it's probably been better if you've been keeping up and doing them each 3 times a week, I guess. Probably some definition and theorem statements as I go back and think about the most important things here. Yeah, you should be able to state any named theorem, certainly. What's the division algorithm? What's Euclid's lemma? I haven't really focused on Euclid's lemma in class, but it is pretty important. And it's got a name. There's our GCD as a linear combination theorem and its corollary. And the corollary, like I remarked, actually is an if and only if. I'm surprised the author didn't write it as an if and only if. A and B would be relatively prime as integers if and only if there exist integers s and t that make this equal to 1. It does work both ways. If you can find integers s and t that make this equal to 1, that would mean they're relatively prime. It means their GCD is 1 because the GCD is the smallest positive integer of this form. And by definition, if that's 1, that means they're relatively prime. There's the definition of GCD and relatively prime. Fundamental theorem of arithmetic's got a name, and it is important, but it's like so unpleasant to write down that probably I would not put it on the exam, just because it's just, well, it's unpleasant. I mean, you know it, you know it's true. You know, given any positive integer, you can factor it as a product of primes in a unique way up to a rearrangement of the orders of the primes. Probably won't have you state that. Yeah, okay, I'll say definitely won't have you state that. Definition of GCD and LCM is important enough to be able to state. And again, because I'm having you state these things, there's no cut in the exam, no open book or notes. Are calculators allowed? I'm not sure. I will tell you if you need a calculator. Probably it would be handy to have, perhaps, but I'm not positive. The applications in chapter 0, about check digits and so forth is not something I would test you on. Should you know about complex numbers? I haven't really focused on it a ton. I've mentioned it in some sort of circumstances, so probably not. Should you be able to state the two principles of mathematical induction? Be more likely to have you use induction rather than state these. And probably the first principle is the more common one to use, and so I'd have you do that. Sometimes the second principle is necessary. Like in example 13, you really can't do it with the first one so clearly, but the second one in example 13 is easier to use. But it's more common to use the first one, so I think I'd test you on the first one in a proof, if I do a proof with induction. There's the factual knowledge about what equivalence relations are. You should be able to state this, but maybe more likely I'd have you use it in a proof or a brief explanation of something. Sometimes I'm looking for proof, sometimes I'm looking for brief explanations or brief reasons. A partition is a definition worth knowing. It's a pretty short definition, actually, so I guess it could be fair game. Perhaps more important just to realize what it is, maybe for a true, false, or multiple choice question. Equivalence classes induce partitions and vice versa, actually. And also understand this notation. The element with a bracket around it stands for the equivalence class containing the element. So any element is always in its equivalence class, which consists of all the elements of the set that are equivalent to A. S is a set here, not necessarily a group. It's just an arbitrary set. This is actually a pretty fundamental fact to know. But again, it's kind of wordy. I probably would not put it on the test as far as stating it. But knowing it as far as true, false, or multiple choice, yeah, I don't know if on the old quizzes if I asked about it. I don't remember. I'm not completely ruling out another multiple choice or true, false question that's not on the old quizzes. I think I did ask some on the exam from 3 years ago, and I don't remember if they're all from old quizzes or not. Not ruling it out. If it seems like it might be a tricky problem, maybe I'd send you an email about it, just giving you a little heads up. Certainly the definition of one-to-one and onto are fair game for stating. Can you state what those are, and can you use them in a proof, like what, for example, what we just did 20 minutes ago? And again, with stating definitions and theorems, I'm not looking necessarily for exact statements, just correct meaning. So it's more important to understand. Chapter 1 got us our first examples of groups. I can turn the page here. Not the official definition of a group, but the idea, the basic idea of it, with the Cayley table here for D4. You know, we've talked about dihedral groups, especially for triangles and squares, a fair amount. You should feel comfortable, not, of course, making this entire table, but doing quick calculations where you draw a little picture to help you. And maybe you just think of it in terms of permutations to figure something out quicker, right? Just the labeling of the vertices, like 1, 2, 3 for an equilateral triangle and 1, 2, 3, 4 for a square, might be quicker to do a calculation. But if I ask you to use this notation, you should be able to use this notation with the rotation and the flips. Interesting stuff about symmetry, but probably not something I test you on. Chapter 2 included the official definition of a group. I think I have put that on old exams as define a group. You know, it's long enough that I probably started for you and you just have to finish it. Make sure you remember that I emphasized in the lectures that binary operation automatically means closure. That's our book's definition of binary operation. It's a function that assigns each pair, each ordered pair of elements to a unique element. Because that is an element of G, by definition, this is closed. Notationally, when you think of it that way, you're thinking of mapping the ordered pair A, B to the product of A and B, A times B or just AB. That's the binary operation that's going on technically. But you know, when we in practice, after this point, we just don't bother with the ordered pair. Right? We just think of it informally as either with a dot or a juxtaposition, putting things next to each other, or maybe if a plus sign if it's an additive group. Then there are lots of examples of groups. I think we have touched on pretty much all these examples at some point. Not all in the same class period, but pretty much all of them I think we've looked at one point or another. Not so much with the complex numbers. I mentioned the vector space thing. This is a vector space. You can add vectors, thinking of them as row vectors here. They could also be thought of as column vectors. Component-wise addition. The operation is addition. When you're thinking of a vector space as a group, which it is, it's an abelian group under addition, you are ignoring the scalar multiplication aspect of it as far as its algebraic properties. I mean, yes, given a vector like this, I can multiply it by 2, which effectively multiplies all the components by 2. But I'm not thinking of that as sort of like this extra operation that I have to think about. It's just a different element of the vector space. Later in the course, in probably late April, we'll go back to vector spaces actually and think of them as an algebraic structure, including thinking about scalar multiplication. These kind of calculations are kind of fun. It's easier when it's Z2 instead of Z7, but yeah, I like that. It's worth remembering the special formula for the determinant of an invertible 2x2 matrix. This is worth remembering, so I'm saying do try to remember this for the exam. Its inverse is 1 over the determinant as long as the determinant is non-zero. Then you swap the entries on the main diagonal and negate the entries on the off diagonal. Excuse me. If you took linear algebra here at Bethel, that's something you definitely should have seen. Dr. Auk, I imagine he talked about it because it is a nice shortcut and it is in the book. And it is in our book too, I'm forgetting where, but if you're doing operations in Z2 or Z3 or whatever, you need to mod by 2 or 3 or whatever as well. And you need to think of this actually, when you're thinking about it in terms of Z2 or Z3 especially, as really being the multiplicative inverse of AD minus BC. Not really right fraction notation. That's what thinking about that example is helpful. This example is good to look at, study, think about. Of course, there's Zn and Un. Nice table summary here. And oh, there's that formula for the inverse. These fundamental facts of groups that you can prove and not taken as axioms because you don't need to take them as axioms because you can prove them. If you can prove something with the axioms, then don't take it as an axiom. They could have been taken as axioms, but you don't need to because it's redundant. You can prove these with the definition of a group. And yeah, you should study these proofs. They're short enough that I could have you ask you to reproduce one on the exam. Notationally, G times itself n times is written as G to the n. In an additive group, you'd write n times G, where G is a group element and n is an integer. And you're not doing times in the usual sense of the word. G might not be a number. Could be a matrix. And the matrix group could be under addition. You have to assume with the groups of matrices under multiplication that the determinant is non-zero. With matrices under matrix addition, component-wise, entry-wise, it can be any matrix of the correct size. N times G when the operation is addition means G added to itself n times if n is a positive integer. Negative G in that context means the additive inverse. And negative 3G, for example, would mean adding negative G to itself 3 times. Where negative G is the additive inverse of G. Sock shoes property, certainly worth knowing and be using whenever you need it. And this works no matter whether the group is abelian or not. Definition of abelian means all elements commute with each other. That's important too. I'll go a little quicker because we're almost out of time. Chapter 3, certainly being able to use the 1- and 2-step subgroup test is probably more important than stating them. You should be able to state the definition of an order, probably more likely to test you to state the definition of the order of an element, including the case of infinite order. Definition of a subgroup, yeah, that's important. So yeah, that's a possibility as well. Probably not state the 1- and 2-step subgroup test, but be able to use them. Some theorems are just more ripe for using than for stating. The finite subgroup test can just get by with checking closure when the group is finite. Definition of this symbol. The definition of that symbol is right there. That's initially just representing this set, but then we proved it was a subgroup, and therefore we call it a subgroup generated by A, and we call it a cyclic subgroup because that's what cyclic subgroups are, is they're subgroups generated by elements, powers of an element. Every group has cyclic subgroups because you can take any element and form the cyclic subgroup generated by that element. Every group has cyclic subgroups. Even the trivial group, E by itself, has a cyclic subgroup itself. In recent days, I've often emphasized that cyclic implies abelian, but abelian does not imply cyclic. You should be able to, the first implication, cyclic implies abelian, you should be able to prove. Abelian does not imply cyclic. You should be able to give an example. It would have to be one of those U groups. And you'd have to know one that's for sure cyclic if you, or not cyclic, I should say. U8 was an example. Center and centralizers. That's a fairly long proof. Yeah, I'm not sure. I mean, you should understand it certainly. Being able to find the center and centralizers for our typical examples that we've done, which is fairly limited examples, Zn, Un, Dn, Sn are the main examples where we think about those kinds of things. And then chapter 4 is all about the details of cyclic groups and the factual information. Some of these theorems are described rather than named, like relationship between the order of AB and the order of A times the order of B. It's one divides the other when you've got a finite group and the elements commute. This is not saying the group is abelian when you look at this here, by the way. It's just saying these two elements happen to commute with each other. Yeah, my thought is in looking over this chapter that the main thing is being able to understand it enough that you just really understand how to apply it in examples. Fundamental theorem of cyclic groups. We did an example Monday, was it? Was the homework problem showing that something like a to the 11th equaled b squared or something like that. There were certain assumptions. It's a little tricky as a homework problem, but we did it in class, and I said you should be able to do it on the exam. The Euler-Phi function is important too. I think these theorems would be more likely to test you about them true-false kind of thing. Theorem 4.4 and the corollary or multiple choice kind of questions with those be most likely, I think. Maybe as a part of a calculation problem as well. Then chapters 5 and 6, we're over time here. Permutation groups and the basics of isomorphisms. The isomorphisms chapter, as all these chapters recently have been, is difficult and long. And we haven't had a chance to talk about all parts of it. You should know what I've said in class here about it and what in the lectures I've said about it, including one more lecture here to watch before next Monday, lecture 12, I think. And things I say, was a review for their exam 3 years ago as well. Things I've emphasized there. If I think of something else I haven't mentioned, I'll let you know. If chapter 6 is on the exam, it'll be on the exam in sort of a light way, not in a ton of depth, not as much depth as you read about in chapter 6. Right. See you on Monday, bright and early.